For those of you who are fans of bridges, particularly suspension bridges, this is James Finley's chain bridge. Built in 1800, it is the original, the grandfather of modern suspension bridge design. You could call this the missing link because it was the connection between the age-old rope bridge and what we recognize as a modern suspension bridge. In this video, we will look at the design of Finley's chain bridge, and in an accompanying video, we will visit the site where it once stood. Around 1800, Americans were spreading out from the cities of the East Coast to inhabit new inland territories. They needed new roads and bridges, but there were few or no expert engineers and little in the way of material or financial resources. That left individuals with freedom to improvise as problems arose. Which in this case brings us to James Finley, a justice of the peace in western Pennsylvania. Without any training in engineering, he proposed, built, and patented a new kind of bridge to fit his rural environment. Taking the simple concept of the rope bridge, he improved on it by making it a suspension bridge with a level road deck suspended from iron chains. Compared to other bridges of the time, a stone arch or wooden bridge, Finley's suspension design was simpler to build, could span a greater distance without extra supporting piers, and cost much less. The rope bridge has been around for a long time. It suits remote places because of its simplicity and small requirement for materials. However, it also has significant limitations. Because the deck you walk on is built directly on the supporting ropes, it follows their curve. So you start walking downhill and end up walking uphill. And they are not very stable. They sag where you step and sway from side to side. It makes a functional but precarious crossing for a person on foot, and, well, a challenge for horse or wagon. Here are the basic features of Finley's proposal. 1. Use iron chains as the main support for the road deck. That gives strength and durability. 2. From the main chains, smaller suspender chains are hung that support a level road deck. No walking up and down hill. 3. To make the road deck more stable, he added extra structural pieces to support the road and a truss-like railing so it didn't sink as people or wagons crossed over. We are fortunate that Finley wrote an article in a magazine called The Portfolio in June 1810. In it, he discussed his thoughts, experiments, and conclusions in a fair amount of detail. Finley put a lot of thought into the details of the design. But there's another key thing we should recognize, which is Finley's approach to the design process. Instead of just using rules of thumb, he made measurements, estimated loads, and figured what was needed to support those loads. That is the process of engineering, and he was one of the first to explicitly follow that process. I'm going to take 3 points from Finley's article to illustrate that point. Point 1. Finley had to answer a simple but important question. How much weight could the suspension chain support? It's easy to figure how much pull an iron bar or chain will bear if you pull on the ends. But what if the chain is horizontal? How much weight can you hang from the middle? To put it more technically, how does the suspended weight translate into tension along the cable? To answer this question, Finley devised an experiment.
This is my version of Finley's experimental setup. The yellow cable here represents the main supporting cable or chain. It's fixed at one end representing the center of the bridge. Each of the two halves of the bridge is the same, so we only need to do half. Then we've taken little weights and added them at equal intervals horizontally across the bridge. That represents the weight of the road deck. Then, where the cable crosses over the pulley, the amount of weight it takes to counterbalance all this weight is a measure of the tension here at the end of the cable, which you'll see is a key thing. From this setup, Finley found 3 important things. The first one was that the height of the tower was important. The taller the tower, the less the tension was along the chain. That means that if he made taller towers, he didn't have to use as much iron in his chain links. But the taller towers also cost money, so he had to reach a compromise. Second thing he found was that if you make the height of the tower 1/7 the total span of the bridge, then the weight suspended on the chain was about equal to the tension in the chain. So he could add up the weight of the wood in the road deck, and then he had a minimum figure for the strength he needed for his chain, minus safety factor. Third thing he found was, if you put a pulley on the other end as well, you can measure the tension is not the same all along the cable. It's lower here in the center and higher over at the tower. So now let's see what a Finley calculation looks like.
Point 2. Figuring out how to size the chain. Finley made a sample calculation we can follow. He proposed a bridge 300 feet in length, 30 feet in width. Wood timbers, he figured, would add up to a load of 140 tons. From a contemporary reference book, he took what he thought was a conservative figure for the strength of wrought iron, 60,000 pounds per square inch. He specified 4 chains made from 1.5-inch square wrought iron bar, which he calculated would give a strength of 540 tons. Finley concluded, the bridge will have an excess of power of at least 400 tons beyond its own weight. But we should pause here and realize that's not really a complete picture. Finley calculated the chains as weighing 20 tons. Adding that to the weight of timber makes a dead load total of 160 tons. You will also need to account for things that temporarily add weight on the bridge, like people, vehicles, and snow, called live load. So Finley made a good try, but his figure is short by the weight of the chains plus the live load. Point 3. When it came time to construct the bridge, Finley had to specify the length of the hanger chains from the main chains to the road deck. He didn't have a mathematical model for the shape of the chain, but he knew it was not the arc of a circle or a catenary. We now know it is a parabola. So, how did Finley find the hanger lengths? He made a scale model. Using a cord, he laid the whole thing out on a fence or wall, hanging weights at the points the hangers would be, and measuring the distance from the horizontal baseline to the curving cord. Again, a practical solution to a tricky problem. In the portfolio article, Finley named 8 chain bridges built according to his design. The first one was built in 1800 near his home in western Pennsylvania, over Jacob's Creek. It was 70 feet long and 12.5 feet wide. He charged $600 for its construction and warranted it for 50 years, excluding the wooden flooring. Probably it looked like this illustration, but with both towers on land. The longest of his bridges was over the Schuylkill River at Philadelphia. Built in 1808, it was 306 feet long with a third pier in the middle. This is a painting of that bridge. His longest lived bridge was over the Merrimack River near Newburyport, Massachusetts. It was built in 1810 under Finley's patent by John Templeman. It stood for 100 years, finally replaced in 1910. The replacement is considered a close copy to the original. After initial success, Finley's design eventually fell out of use. The estimate is that maybe 40 bridges were built more or less according to the Finley design. The next improvement in suspension bridges was making the cable from multiple strands of wire, as later pursued by Charles Ellet and John Roebling. Judge Finley died in 1828. Even though he didn't have the full engineering analysis down, his practical methods and thoughtful design process warrant recognition as an early innovator and engineer. In 2008, Pennsylvania dedicated an official state historical marker in honor of Finley and his 1808 suspension bridge patent. In Part 2, we will try and locate the site of the famous Jacob's Creek Bridge and go for a visit. See you at the bridge.